Hello guys, welcome to lecture 5 of our lecture series, Chemistry for Engineers. Today we'll be looking at gases. So our objectives for today will include looking at the physical properties of gases, and as we've discussed in our last lecture, looking at the 3 states of matter, solid, liquid, and gas. We know that gases tend to occupy the space of the container, and we can also add that gases are really small particles, very small atoms that moves quite rapidly. They are compressible. So for example, if they are contained in a container, you can compress them. They're expandable, meaning that if they're also in a container, you are able to expand in terms of space. And we call that expandability. They have low density. They can be mixed with other gases. They also exert pressure on the wall of the container or a container in which they are contained, as we can see with a hot air balloon or just a balloon. There are different gaseous compounds, and as we know, a compound is a substance made up of 2 or more atoms, and as we can see, gases tend to be diatomic in many cases, even though they don't readily form relationships or bonds with other molecules. Gases such as hydrogen, nitrogen, oxygen, chlorine, bromine, iodine, these are diatomic molecules. And from our first lecture, we actually went through the noble gases such as helium, neon, argon, krypton, xenon, radon. We also looked at hydrogen, nitrogen, oxygen, chlorine, bromine. As much as mercury and bromine are not gases, they tend to exist in liquid state, and we will see that mercury is used in many experiments that include exploration of gases as it relates to pressure, because mercury does not readily bind with other atoms, especially gases. We will also be looking at ideal gas law, which looks at the different states and behavior of gases as it relates to pressure, volume, temperature. We will eventually understand that there are different laws as it relates to the behavior of gases, such as Boyle's law, Charles' law, Avogadro's law. Boyle's law states that pressure and volume has an inverse relationship. So if the pressure increases by 2-fold, then the volume should decrease by 2-fold. If the volume increases by 2-fold, then the pressure decreases by 2-fold. Thus, the formula is P1 times V1 equals P2 times V2. Charles' law describes the relationship between volume and temperature. Always remember that temperature is measured in Kelvin. The volume of an ideal gas is proportional to its temperature. Therefore, V1 divided by T1 is equal to V2 divided by T2. Avogadro's law looks at volume and the number of moles of an atom, volume and atomic mass. Therefore, equal volume of different gases contain equal number of molecules. In a mixture of gases, each constituent gas will have its own contribution of pressure. We basically call this partial pressure of gas. In essence, the pressure exerted by an individual gas among a mixture of gases would be the partial pressure of the mixture. In our last lecture, we looked at stoichiometric calculations. In this case, we'll also be looking at stoichiometric calculation as it relates to gases. Kinetic theory of gases looks at gases in its non-ideal state. Kinetic energy describes the energy that is emitted when an object is moving. And as we should know, a property of gas is that they're in constant motion. They're always moving. Therefore, they should be able to exert some type of kinetic energy as well. This relates to gases at different temperatures. So we will see that the movement of gases is highly dependent on temperature. At room temperature, gases tend to move 1,000 miles per hour. The molar mass of a given molecule or gaseous molecule will determine their speed. A more complicated way of expressing this is through assessing the distribution of speed of gases. This includes the distribution of velocity or speed of a molecule. Because gases are always in constant motion, Maxwell-Boltzmann distribution of speeds was invented invented to predict the distribution or velocity of the molecule or gaseous molecule relative to temperature and the number of molecules. So here we can see we have group 18 elements are known as the gases. We also have hydrogen, which does not belong to any group or class, where we find our group 1 element. We have nitrogen, oxygen, as well as a few group 17 elements. Very important, most of our gases exist as diatomic molecules. For example, as we can see here, hydrogen, nitrogen, oxygen, chlorine, bromine, fluorine, as well as iodine. As we know, gas is in the air. Air is all around. The chemical composition of air contains various gases. Air is a mixture rather than a pure substance, a mixture of nitrogen and oxygen, which accounts for 99%. Other important components are carbon dioxide, water vapor. We also know that there is helium, chlorine, neon, krypton, methane. The amount of water in the air varies from place to place and day to day, as described by humidity. Here we can see our diatomic elements as well. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine are all diatomic elements. Have no fear of ice cold beer. So as we mentioned before, nitrogen and oxygen alone make up roughly 99%. If you sample the air in a modern city and analyze it, you'll find many different compounds. The composition of 1 cubic meter of sample of dry air at 25 degrees Celsius at normal atmospheric pressure contains the following gases in mole: nitrogen at 31.92 moles, oxygen 8.567, argon 0.38, carbon dioxide 0.013, and other trace gases. Trace compounds can be linked to natural sources, but most are directly attributable to human activities like transportation and manufacturing. The Environmental Protection Agency identified 6 principal criteria for pollutants: carbon monoxide, nitrogen dioxide, trioxygen or ozone, sulfur dioxide, lead, and particulate matter. In many cases, the allowable level of these pollutants correspond to less than 1 part per million, which means 1 molecule per every million molecules of air. One of the criteria pollutants, nitrogen dioxide, which is emitted as a part of the exhaust from a motor vehicle. So at high temperatures at which engines operate, the nitrogen and oxygen gases present in air react with each other to form a variety of nitrogen oxide. So the nitrogen and the oxygen reacts at very high temperature to produce nitrogen oxide. When engines run hotter from standing in, for example, traffic jam, they produce nitrogen oxides. Once it is present in the air, nitrogen dioxide is known to attack the membranes in your lung. Nitrogen dioxide molecules absorb some portion of visible light of the sun, leaving the colors that produce brown to pass through. So that's how you get the smog, because the molecule absorbs some portion of the visible light. Light energy from the sun can also initiate chemical changes through what is known as a photochemical reaction. So light energy from the sun can also initiate chemical changes from what we call photochemical reaction. So here we can see a photochemical smog that is produced by nitrogen dioxide due to solar radiation. And as you can see, this nitrogen dioxide goes on to contribute to our ozone or oxygen trioxide or trioxygen. It also contributes to various aldehydes, nitric acid as well. For nitrogen oxides, these photochemical process leads to products that can further trigger the formation of the ground level ozone, as we've mentioned before. This is the ozone or trioxygen. But nitrogen oxides cannot generate ozones on their own. The key additional components that are needed are molecules collectively referred to as volatile organic chemicals, or VOCs or VOCs. Organic chemicals contain predominantly carbon and hydrogen. They tend to evaporate easily. They combine 2 traits, meaning they are carbon-based molecules that evaporate readily. Many different VOCs are present in urban air, and the primary source of these chemicals is fuel. Very important though, volatile organic chemicals can come from a variety of sources such as plants, paint strippers, cleaners, disinfectants, spray, nitrogen compounds, carbon compounds, and as we can see, herbivores and various various organic compounds. All combustion engine releases some volatile organic chemicals when they are operating, and older vehicles tend to release more. Chemical reaction between photochemically activated nitrogen oxide and volatile organic compounds can give rise to a mixture of gases that is collectively referred to as smog. So if you mix the nitrogen oxide and other gases, you basically end up with a smog. And here you can see different types of smog and different sources of volatile organic compounds. So as we mentioned before, many of the compounds in smog are irritants to the lung. Ozone 3 or trioxygen is the most significant problem. When present at the ground level, ozone poses a range of health hazard even for healthy young adults. People with respiratory problems such as asthma are particularly susceptible to the problems associated with ozone. Nitrogen dioxide and volatile organic compounds lead to the generation of O3 or trioxygen. So NO2 and VOC leads to the generation of O3. The levels of nitrogen oxides and VOC tend to rise in the morning hours, especially due to emission from vehicles. The presence of both NOx and VOX lead to increased production of lung irritants such as ozone, whose level goes through a maximum during the afternoon. Here we can see a visual representation of nitric oxide, nitrogen dioxide or nitrogen oxide. This is also important in the morning as well. Here we can see the lung irritant, that is the trioxygen, that is usually present in the evening. As we know from our first lecture that gases expand to fill the volume of the container. Gases have much lower density than solids and liquid. They are highly variable in terms of densities depending on the conditions such as the temperature as well as pressure. They mix with each other readily and thoroughly. Gases change volume dramatically with changing temperature. So here we can see different gas laws. We mentioned Boyle's law, where pressure and volume are inversely proportional. So as the pressure doubles, the volume is half. As the volume doubles, the pressure is half. So with Charles' law, the volume is proportional to the temperature. So if there's an increase in volume, there should be an increase in temperature. If you inflate, gas expands or contract by the same factor that temperature increases or decreases. So with Charles' law, we're basically seeing the volume is proportional to the temperature. If you have an increase in volume, you should have an increase in temperature. If you have a decrease in volume, you should have a decrease in temperature. In Gay-Lussac's law, volume is constant. This states that pressure is directly proportional to temperature. As temperature rises, so does the pressure. So again, properties of gases include they occupy the volume of the container, they have lower densities, their density vary based on temperature and pressure, they mix with each other, and their volume change dramatically with the change in temperature. The fact that gases expand to fill the available volume, exhaust gases released from a car or an industrial plant will readily spread throughout the surrounding area. Similarly, the fact that gases mix readily with one another means that once they are present, traces of gaseous pollutants will usually be difficult to separate from air. So here we see a representation of Charles' law where T1 and V1 is equal to T2 and V2, which means that where there's an increase in temperature, there's also an increase in volume. So where there is a decrease in temperature, there is a decrease in volume. Where there is an increase in temperature, there is an increase in volume. So we spoke about Boyle's law, Charles' law, Avogadro's law. So the equation for the ideal gas law is PV equal nRT. P is the gas pressure, V is the gas volume, N is the number of mole of gas that is present, T is for temperature, and this should be in Kelvin. R is a constant called the universal gas constant because its value of 0.08206 liter atmospheres per mole per Kelvin is the same. So this constant will always be the same for any gas. We're basically showing the same thing here. P is the pressure of gas, V is the volume of the gas, T is the temperature of the gas, N is the number of moles, R is the gas constant. And as we've said before, this is represented as 0.082 in the form of liters per atmosphere per Kelvin per mole, or 8.314 kilojoules per mole. We know that the gas law looks at pressure, volume, temperature, gas per mole. Pressure is defined as force exerted per unit area. For atmospheric pressure, force can be attributed to weight of the molecules of air that are attracted to the surface of the planet by gravity. The force can be attributed to the weight of the molecules of air that are attracted to the surface of the planet by gravity. The existence of atmospheric pressure may not be apparent, but can readily be demonstrated by removing the air from a container. So in an experiment where you heat the container and you remove the air from the container, immediately transferring this container into cold water will demonstrate the effect of the atmospheric pressure crushing the container. Pressure is force divided by area. Force is pressure times area. Area is force divided by pressure. For atmospheric pressure, the force can be attributed to the weight of the molecule of air that are attracted to the surface of the planet by gravity. So this basically looks at the molecule being pushed down to the surface by gravity based on density. The existence of atmospheric pressure may not be apparent, but can be readily demonstrated. So pressure can be measured through measuring the mass in a column or a cylinder that extend from the surface of the earth towards space, where 1 cubic meter column of air gives a mass of 10 to the 4th kilogram, with 1 atmosphere in terms of pressure at the surface. Even an apparently sturdy container collapses under the pressure of the atmosphere when the air inside is no longer supporting the container. So remember that a container with air is constantly being supported by air or gas molecules due to the kinetic effect of these molecules. Because they're in constant motion, they keep bouncing off the sides of the containers, and because the total weight of the molecule increases as the number of molecules increases, the atmospheric pressure changes as a function of altitude. So because here we have a lower pressure inside, with this being suspended in water and being able to respond to the high atmospheric pressure, this results in water being pushed into the can by air pressure. This results in the can being crushed. At sea level, 20,320 feet of atmospheres are above us than at the summit of Mount McKinley, and the atmospheric pressure at sea level is much higher than at the mountain top. So here we can see pressure in PSI and the altitude. But what about gas trapped in container? We can think about this by considering air in a balloon. It exerts pressure uniformly on all the walls of the balloon without regarding to direction. Clearly, this cannot be due to gravity. So with air in a balloon, the pressure is sustained by the kinetic properties of gases, where molecules collide continuously on the edges of the balloon. The pressure is sustained in the balloon due to the collision of gas molecules with the object or the corners or the walls of the balloon. The molecules keep colliding with the inner wall of the balloon, and that's how we create pressure. So basically, the constant collision keep the balloon inflated. We've looked at Charles' law before, but as you already know with my lectures, there's always a lot of repetition and always a lot of emphasis. So each molecular collision imparts a small force to the container, and when these tiny forces are summed across the vast number of gas molecules present, they can produce the macroscopic force that leads to gas pressure. In Charles' law, V1 divided by T1 equal V2 divided by T2. In this case, pressure is constant. As the temperature increases, the volume increases. Because pressure is one of the important measurable properties of a gas, several different ways have been devised to measure it, beginning with the barometer. The essential feature of a standard barometer is a long tube that is closed at one end and is filled with mercury. Mercury is used because it has a high density and does not react chemically with common gases. So here we can see we have a reservoir with mercury. We have a cylindrical tube as well with mercury, and here we have a vacuum. So here we actually see at sea level we have air pressure. Because the mercury is dense and it does not react with gases, the air tends to push down or exert some form of a pressure on the mercury in the container, and this basically results in a vacuum at this end. So this basically automatically produces the atmospheric pressure, and here we can see the sea level pressure at 76 centimeters or 29.92 inches. When the mercury filled tube is inverted in a pool of mercury, some of the liquid but not all runs out of the tube. The closed end of the tube is then under vacuum, which means that the pressure in this region is greatly reduced. If this end of the tube is open, all the mercury pours out. So here we can see the vacuum as well, and this is basically just a repetition with the atmospheric pressure indicated here. The pool of mercury is exposed to the atmosphere and thereby experiences the pressure of air weighing down on it. The column of mercury in the tube has a vacuum over it and so has no pressure weighing down on it. So here we can see the measurement of pressure at sea level, 760 millimeters of mercury. When the atmospheric pressure decreases from weather variation, the decrease will cause the column to shorten to maintain the equality of pressure at that point. Near sea level, the column of mercury is typically 730 millimeters and 760 millimeters in height of mercury. So pressure is measured in Newton, in N or Newton square meter. The unit has also been named Pascal or PA. 1 Newton is roughly the force exerted by gravity on 1/4 pound object. So this is the pressure formula. So pressure is force divided by area. F divided by A. F or force is measured in Newton. A is the area measured in meter squared, while pressure is measured in Pascal. So 1 Pascal is 1 Newton per meter squared. So for example, a force of 10 Newton acts over an area of 2 meters squared. What pressure is created by the force? So we're looking at pressure and we say pressure is force divided by area. So if we get the force, which is 10, and we get the pressure in meter square, it would be 10 divided by 2 meter square or Pascal. So the pressure is 5 Pascal or 5 Newton per meter square, 5 Newton per square meter. So both of these units appear to express pressure as a length, which can be confusing because we define pressure as force per unit area. The height of the mercury column in a barometer is directly proportional to the applied pressure. So the higher the pressure exerted by the atmosphere, the higher the column of mercury. As a result, it can be common to report pressure directly in terms of measured height. So here again, 1 atmosphere is basically 1.01325 times 10 to the 5th Pascal, or a kilopascal to atmosphere. 1 atmosphere is equivalent to 101,325 kilopascal. 1 atmosphere is equivalent to 760 millimeters of mercury, or 760 torr, or 1.01325 bar, or 1013 millibar, or 14.7 psi. So 1 atmosphere, 14.7 psi. So in spite of this confusion, the millimeter unit is still widely used and has been given an additional name, the torr. We can consider 2 units equivalent. 1 torr is 1 millimeters of mercury, which is equivalent to 1 atmosphere. 1 atmosphere is equivalent to 760 millimeters of mercury. 1 atmosphere is equivalent to 760 torr. Another unit of pressure arises from the importance of atmosphere. The average pressure at sea level is close to 760 torr. The common observation of an apparent average atmospheric pressure leads to the definition of a unit called atmosphere, ATM, which was set equal to 760 torr. As the science has become more precise in measuring it, this equivalent still remains. 1 atmosphere is equivalent to 760 torr exactly, and 1 atmosphere is also equivalent to 760 760 millimeters of mercury, and 1 torr is equivalent to 1 millimeters of mercury. 1 atmosphere is also equivalent to 760 millimeters of mercury, is equivalent to 1.01325 bar, or 1013.25 millibar, or 14.7 psi. But the definition of unit atmosphere has since been changed to reflect SI unit. It is now defined in terms of Pascal. So 1 atmosphere is 101,325 Pascal exactly. Combining the last two relationship gives us formal definition of the torr as well. So 760 torr is equivalent to 101,325 Pascal. Gas naturally follow from higher pressure to lower pressure, and pollutants are often produced in a high pressure environment, such as in the cylinder of an auto engine or a reaction vessel in an industrial processing plant. When gases are released from high pressure environments, they disperse rapidly into the surrounding air. The pressure difference helps speed the spread of the pollutant. So here we have the ideal gas versus the non-ideal gas. The ideal gas exists at high temperature, moves pretty quickly at high temperature but in low pressure. For the non-ideal gas, you have intermolecular connection or intermolecular interaction. So basically, with low temperature and high pressure, there is more communication between each molecules or particles. So if you change the temperature, the pressure or volume of a gas container, it will result in a dramatic response from the gas. All gases respond to these physical changes in the same way despite their chemical difference, and the gas law equation allow us to calculate the impact of a particular change. So again, Charles' law basically looks at the constant, which is pressure in that case. So the physical states of gas, as we know, physical states include pressure, volume, temperature. For Charles' law, where pressure is a constant, the volume of the gas is directly proportional to the temperature. So if you increase the temperature, you will increase the volume. If you decrease the temperature, you will decrease the volume. And in this case, pressure is constant. Charles investigated first the relationship between temperature and volume in the early 19th centuries. He noted that when he plotted volumes versus temperature for different amount of gas, the resulting lines converge to the same temperature at zero volume. So here we can see V1 divided by T1 equal V2 divided by T2. When pressure is constant, this equation is used to compare different conditions on the same substance. And in this case, temperature is directly proportional to volume. Volume divided by temperature equals K constant. K equal proportionally constant. And in this case, pressure is constant. This fact was used to establish the Kelvin temperature scale. Once the temperature is expressed on Kelvin scale, the volume and temperature are directly proportional, and the observation is known as Charles' law. And that's why we said that with all these equations and calculation, you basically have to convert from degrees Celsius or degrees Fahrenheit to Kelvin. When pressure is constant, P1, P2, P3 is constant, volume is divided by temperature. Volume and temperature is directly proportional, and this is in the case of Kelvin. So if you're given the value in degrees Celsius, all you need to do is to add this to 273, which is 0 degrees Kelvin. That basically converts the temperature to Kelvin. Boyle's law studied the relationship between gas pressure and volume and noted that for any gas sample, when pressure increases, the volume decreases. So there's an inverse relationship. Or when volume increases, pressure decreases. Thus, Boyle's law states that when the temperature is constant, pressure and volume are inversely proportional. Temperature is constant, and when the volume decreases, the pressure increases. Or if the pressure increases, the volume decreases. So here we can see that temperature is constant on both sides, and with an increase in volume, you have a decrease in pressure. With a decrease in volume, you have an increase in pressure. Avogadro's law similarly states that volume of gas is proportional to the number of moles moles or molecule of the gas present. So in this case, temperature and pressure is constant, equal volume of gases contain equal number of molecules. So temperature and pressure is constant in this case, and V1 divided by N1 equal V2 divided by N2. If the volume of gas is low, or the molecules are low, or the moles or the atomic weight should be lower. If the volume is high, then the number of molecules are also high, which means that the moles is supposed to be high as well, or the number of moles or the atomic weight should be high as well. As long as we know the ideal gas equation and know how to work it, we can easily solve problems that might also be approached using any of the individual gas laws. To do this, just start by identifying all the parameters which we already discussed before, P, V, T, or N, that do not change. You basically will have to identify all the parameters that are constant. So the ideal gas law again is PV nRT. P is basically pressure, usually in atmosphere. V is volume, usually in liter. N is the number of moles. R is the universal constant, which is 0.082 liters of atmospheres per mole in Kelvin. Remember, so for pressure in atmospheres, remember that 1 atmosphere is equivalent to 760 torr, or 101.3 kilopascal, or 101,325 pascal. Remember that temperature should also be in Kelvin. And for temperature in Kelvin, if you're given degrees Celsius, you can simply just add the temperature in degrees Celsius to 273 Kelvin, and that will basically give you the temperature in Kelvin. For milliliters, you can simply convert this to liter, as 1000 milliliter gives you a liter. When you get a problem, first you need to elucidate what you need to extrapolate. So if it is that you need to find pressure or temperature or volume, based on what is being asked, you basically have to rearrange what is constant will be on one side, what is not constant will be on the other side. So here again, the R is called universal gas constant. Its value and units depend on the units used for pressure, volume, and temperature. So remember, for the ideal gas law, PV, which is pressure times volume, equals nRT. N is the number of moles, R is the constant, T is the temperature in Kelvin. Because the product nRT remains constant, we know that PV must be constant as well. This tells us that the product of P times V must be the same before and after the change. So we can write P1 V1, or P1 times V1 equals P2 times V2. We know this is Boyle's law. In Boyle's law, PV is constant, pressure and volume is constant, and the equation, as we've mentioned before, P1 times V1, which is equal to P2 times V2. So this basically states that there is an inverse relationship between pressure and volume. Pressure and volume as an inverse relationship. Charles' law describes the relationship between volume and temperature. V1 divided by T1 equals V2 divided by T2. So if the volume decreases, the temperature decreases. So if the temperature decreases, the volume decreases. If the volume decreases, the temperature decreases. So in essence, V1 divided by T1 will be equal to V2 times T2. Avogadro's law deals with the number of moles or mass. So if the volume increases, the number of moles or the mass increases as well. But if the volume decreases, then the number of moles or mass decreases. So remember that N, the number of moles, remember that R is the constant. So the combined gas law is basically the ideal gas law that combines all the other laws. So for example, so if we basically write the ideal gas law, which is PV equals nRT, we can divide PV by NT. This will be equal to PV divided by NT, where R is constant. So in essence, P1 V1 divided by N1 T1, and R remains constant. Similarly, P2 times V2 will be equal to N2 T2, where R is also constant as well. So we basically can say P1 V1 divided by T1 is equal to P2 V2 divided by T2. And remember that N is the number of moles. So this would basically be the combined gas law. Let's try a problem. A common laboratory cylinder of methane, for example, has a volume of 49 liters and is filled to a pressure of 154 atmospheres. Suppose that all of the methane from the cylinder is released and expands until the pressure falls to 1 atmosphere. What volume would the methane occupy? In this case, N and T are constant, so the number of moles of methane will be constant. The temperature is constant, and R is always constant, as we remember, which would be equivalent to 0.082. Therefore, P1 V1 will be equal to P2 V2. So we're basically trying to find the volume of V2. So we can use the Boyle's law to figure out this equation. So V2 equals P1 V1 divided by P2. So we know that P1 is 154 atmospheres. V1 is 49 liter. And remember that in atmospheres, if the pressure is expressed in atmosphere, the volume has to be expressed in liter as well. So we know that P2 is 1 atmospheres as well. So if we fill in the equation, V2 would be equal to 154 atmospheres times 49.0 liter divided by P2, which is 1 atmospheres. So this basically gives us 7,546 liters. So the volume that methane would occupy would be 7,546 liters. So the pressure falls by 154 atmospheres, which basically means that it fell to 1. You should have a proportional increase in volume, or an increase of 150 times. So here we have another example problem. A sample of CO2 gas has a volume of 575 cubic meter at 752 torr and 72 degrees Fahrenheit. What is the mass of carbon dioxide in this sample? Since the problem involves a gas, we can attempt to use ideal gas law to find the number of moles. We're given values for volume, which is 575 cubic meter. We're given values for pressure in torr, which is 752 torr, and we're given temperature in Fahrenheit, which we know that we'll have to convert in Kelvin. So we will have to be able to solve N, which is the number of moles for carbon dioxide. So let's start with volume. So we have volume V equals 575 cubic meter, which is 575 milliliters, If we convert this to liter, we basically get 0.575 liters. So remember that 1 atmosphere is equivalent to 760 torr. So you can either convert it to atmospheres or you can leave it as torr. So say for example, we want to convert it. We can say 752 torr divided by 1 times 1 atmosphere, which is equivalent to 760 torr, which will give us 0.98 atmospheres. We will also have to convert to Kelvin. To convert from Fahrenheit to Celsius, temperature would be equal to 72 Fahrenheit, which we have here, minus 32 times 5/9 times 32. And this basically gives us 22 degrees Celsius. So you have to minus 32, which basically gives you the degrees in Celsius. To convert this to Kelvin, all you need to do is to add 273. This will basically give us 295 Kelvin. So we know what volume is in liter, we know what pressure is in atmospheres, we know what temperature is in Kelvin. So now we need to find the mass of carbon dioxide. And as we know from our last lecture, 1 CO2 has 1 carbon and 2 oxygen. So the molar mass of carbon is 12. The molar mass of oxygen is 16, and this would be 16 times 2 because it's 2 oxygen. So here we should have a plus. This will basically give us 44.0 grams per mole. So we're trying to find the number of mass, which is N. So N would be equal to pressure times volume divided by R, which is a constant, times temperature. We basically can use atmospheres or we can use torr, the torr that was given. Generally, we tend to use atmosphere, but for this case, I'll use torr. So this would be 752 torr. And the volume is 0.575 liters. Divide by the constant in torr. So the constant in torr, so remember that the constant is 0.082 atmospheres. We'll have to convert that to torr. So you basically can times 752 by 0.082 to basically convert this to torr. We'll have to basically times 752 torr times 0.082 in atmospheres, which will basically give us 62.37 liters in torr per mole per Kelvin. So here we have 62.37 torr per mole per Kelvin times temperature, which we know is 295 Kelvin, which gives us 0.023. So remember that we want to find the mass of carbon dioxide, and we already know the molar mass of CO2 is 44. So this would be 44 times 0.02. So it would be 44 grams per mole of CO2. So this will give us 1.034 grams of CO2. So the mass of carbon dioxide would be 1.034 grams of CO2. So 1 gram is a pretty small mass, but it's basically reasonable for a small balloon. When you have a mixture of gases, you might want to find the partial pressure of a given gas. So for example, if you have nitrogen, oxygen, you might want to find the partial pressure of nitrogen or oxygen or vice versa. So pressure will, in this case, will be P equals nRT divided by volume. Pi, where I is basically indicating the gas, the specific gas that we refer to, would be equal to NIRT divided by volume. So this is how you find the partial pressure of a gas. So remember that Ni would be the number of moles of that particular gas. Consider a sample of air for simplicity. Assume that it consists entirely of nitrogen and oxygen. Assuming that the air behaves ideally, its pressure can be expressed using the gas law. So in this case, it would be pressure equals nRT divided by volume. N is the total number of moles of air present, but the total number of moles will simply be the sum of moles of each component. The total number of moles, for example, of nitrogen and oxygen would be N equals N2 plus NO2. So the total number of moles of nitrogen, for example, nitrogen has an atomic mass of 14. So this would be 14 times 2 plus oxygen as an atomic mass of 16, which would be times 2. So this would be 60. So in this case, it would be the total number of moles, for example, would be 60 times the constant times the temperature divided by volume. So here we have a few example problems in finding the partial pressure of a gas. Not all pollution is due to human activity. Natural sources, including volcanoes, also contribute to air pollution. To generate a mixture of gases similar to those found in volcanoes by introducing 15 grams of water vapor, a scientist tries to generate a mixture of gas similar to those found in a volcano by introducing 15 grams of water vapor to 3.5 grams of sulfur dioxide and 1 gram of carbon dioxide in a 40-liter vessel held at 120 degrees Celsius. Calculate the partial pressure of each gas and the total pressure. So you'll have to calculate the partial pressure of water, sulfur dioxide, and carbon dioxide. So for all gases, we know that temperature is 120 degrees Celsius. You'll have to convert that to Kelvin, which is equal to 393 Kelvin. The volume is 40 liters, so 15 grams of H2O. And we already know from our last lecture in stoichiometric calculation, how we derive 18 grams of H2O. Hydrogen has an atomic mass of 1, so that would be 1 times would basically give us 2. Oxygen has an atomic mass of 16, so that would be 16 plus 2, that basically gives us the 18 grams. So it would be 15.0 grams of H2O times 1 divided by 18 grams of H2O gives us 0.833 mole. To find the partial pressure, so remember that Pi is equal to NIRT divided by V. So to find the partial pressure, we have 0.83 moles of H2O times the constant, which is 0.082 in liters per atmospheres per mole per Kelvin. We're given a temperature of 121 degrees Celsius, which is converted to 393 Kelvin. So this would be times 393 Kelvin divided by the volume, which is 40 liters. This basically gives us a partial pressure of 0.672 atmospheres of H2O. We're given 3.5 grams of sulfur dioxide, and recall from our last lecture as well, the atomic mass of sulfur is 32. Oxygen we already know is 16, so 32 plus 16 times 2, that gives us 64 grams of sulfur dioxide. And if we 3.5 grams of sulfur dioxide times 1 mole of sulfur dioxide divided by 64.1 grams of sulfur dioxide gives us 0.055 mole. To find the partial pressure of sulfur dioxide, 0.055 mole times the constant, which is 0.0826 liter per atmosphere per mole per Kelvin, times 393 Kelvin divided by 40 gives us 0.044 atmospheres. And this would be the partial pressure of sulfur sulfur dioxide. For CO2, we're given 1 grams. So 1 grams of CO2, we know the atomic mass already is 44.0 grams. So 1 grams of CO2 times 1 mole of CO2 divided by 44 grams of CO2 gives us 0.023 moles. To find the partial pressure of CO2 using our equation for partial pressure, we basically use 0.023 mole times 0.826206 liters per atmosphere per mole per Kelvin, which is a constant again, times 393 Kelvin divided by 40 liters. And this basically gives us 0.018 atmospheres. So to gain the total pressure, or P total, we basically now will have to add the partial pressure of each. Partial pressure of H2O, sulfur dioxide, as well as carbon dioxide. So the partial pressure of H2O, we basically calculated 0.672. So it would be 0.672 plus 0.044 atmosphere, which is that for sulfur dioxide, and 0.018 atmosphere that we calculated for partial pressure of carbon dioxide. So this basically gives us a total pressure of 0.734 atmospheres. The ideal gas law provides a relationship between the number of mole of gases and some easily measurable properties such as pressure, volume, and temperature. We can also be given a stoichiometric reaction where we have two reactants reacting to give us a product, and in this case we'll have to balance the equation. So potassium chlorate in the form of a solid heated produce potassium chloride, which will basically produce oxygen gas. Here's an example of a stoichiometry problem. When an experiment required a source of carbon dioxide, a student combined 1.4 grams of sodium bicarbonate NaHCO3 with excess hydrochloric acid. If the carbon dioxide produced is collected at 722 torrs and 17 degrees Celsius, what volume will the gas occupy? With any stoichiometry problem, as we've mentioned before, we will need to start with a balance equation. For the reaction to be sure, we use the correct mole ratio. Sodium bicarbonate reacting with hydrochloric acid gives us sodium chloride, water, and carbon dioxide. We start with a balance equation, and we can check if this equation is balanced by counting the atoms. So we have one sodium on the side of the product. We have two hydrogens, one hydrogen here as well as one hydrogen here, and we have two hydrogen on the side of the product. So we basically have one carbon on either side, three oxygen molecule, three oxygen. So here we have O2 plus 1, that will give us 3, and 1 chloride ion. 1 chloride on the side of the reactant and 1 chloride on the side of the product. So here we're asked to calculate volume. Volume will be V equals nRT divided by pressure. So here we'll have to convert the molar mass of 1.4 grams of sodium bicarbonate. So this will be 1.4 grams NaHCO3, and we use the mass ratio. So we know that 1 mole NaHCO3 will be equivalent to 84 grams of NaHCO3 times 1 mole of CO2 divided by 1 mole. So this is basically a 1:1 ratio of NaHCO3. And this basically gives us 0.017 moles of CO2. Now you can use the ideal gas law to find the volume, but remember that you'll have to convert from degrees Celsius to Kelvin. So V equals nRT, which would be equal to 0.017 moles of CO2 times 0 times the constant, which is 0.0826 liters. And remember that this is in atmospheres per mole per Kelvin. and 17 degrees Celsius converted to Kelvin, and you can do your own calculation, would be 290 Kelvin, 290. No, this doesn't look like 290, but it's 290 K, 290 Kelvin, and this would be divided by the pressure. And remember that you have to convert the pressure from pore to atmospheres. So in this case, it would be 722 divided by 1 times 1 divided by 760, which is 1 atmospheres, which basically gives us 0.95. So if you multiply all these factors, divide by 0.95, you basically end up with 420 mils. So the volume that the gas will occupy is 420 mils or milliliters. The kinetic molecular theory actually operates on the 5 assumptions. So gas particles are actually in constant random straight line motion. Particles are separated by great distance. Collisions are rapid and elastic. There are no force between particles, and the total energy remains constant. So the average kinetic energy is directly proportional to temperature. As temperature goes up, so does the kinetic energy. Non-ideal behavior is frequently seen in gases as very high temperature. So basically, the kinetic theory looks at gases in their non-ideal state. Non-ideal behavior is also frequently seen in gases when the pressure is very high. So this can be seen when gases are confined to an engine or a cylinder or a processing plant. So this is basically looking at the temperature increase. So when a gas is confined in a space with an increase in temperature, there's an increase in pressure. Pressure increases because the gases will move around quite quickly. With a decrease in volume, the wall area decrease, there's also an increase in pressure. If you increase the volume, you increase the number of molecules, and basically the pressure will be constant in this case. The molecules in a gas exert force when they collide with the wall of a container, and this accounts for the relationship between pressure and volume. So again, the pressure and volume occur because the molecules of the gas are actually colliding with the container. As the volume of the container increases, the walls move further apart, so each molecule will strike the walls less often. So the more you confine the gases into a space, the more they will collide with the container. So that would basically be that you decrease the volume and increase the pressure. Each molecule will exert less force on the wall in a given time interval, reducing pressure. So the kinetic theory is consistent with the inverse relationship between pressure and volume that we've seen in the gas law equation. So again, this is just a bit of repetition. The molecules in a gas exert force when they collide with the walls of the container, and this accounts for the relationship between pressure and volume. As the volume of the container increases, the walls move further apart, and so each molecule will strike the wall less often. Thus, each molecule will exert less force on the wall in a given time interval, reducing pressure. The Maxwell-Boltzmann distribution looks at the speed of each gas collision, and it also takes in account the density as well. The distribution function that describes the speed of a collection of particles is known as the Maxwell-Boltzmann distribution of speed. Here, the x shows a fairly familiar quantity, speed in meter per second. The y shows the fraction of all molecules in sample that would be traveling at a particular speed. So the y-axis basically shows the particles traveling at a particular speed in meters per second. The y-axis shows the quantity in the form of density. The distribution of molecular speed of CO2 molecules at different temperature are shown. The quantity on the y-axis is the fraction of gas molecule moving at a particular speed. Notice that as the temperature increases, the fraction of molecule moving at higher speed also increases. So here we can see the temperature in Kelvin. So at 1000 Kelvin, the peak moves more towards the right. Speed basically increases as the temperature increases. So the gas molecules tend to move faster at higher temperature. And here we can see at 300 Kelvin, the gas particles are actually moving much slower. So the speed of the gas particles or the speed of the molecules are naturally decreased at this point. So at high temperature, we see that the peak in the distribution shifts towards higher speed. This is entirely consistent with postulate number 5, which states that the kinetic energy of molecule must increase with temperature. Furthermore, postulate 5 also says that the kinetic energy does not depend on the identity of the gas, but the mass of the gas molecule clearly depends on their identity. So the identity of the gas doesn't matter, but the mass actually do matter. You can readily see that on average, lighter molecules travel faster than the heavier molecules. So the kinetic energy theory will state that at high temperature, the gas molecules move faster. And also if the molecules are lighter, they tend to move faster. So if there's more density, the molecules tend to move a bit more slowly. So here we can see the distribution of molecular speed of 4 different gases at the same temperature at 300 degrees Kelvin. The quantity on the y-axis is the fraction of gas molecule moving at a particular speed. Notice that the molecular mass describes the fraction of molecule moving at higher speed. Notice that as the molecular mass decreases, the fraction of the molecule moving at higher speed increases. So here we can see helium, which is the lightest or has the lowest density. So helium has an atomic mass of 4, H2O of 18, nitrogen 28. This is 28, this is 32. So as you can see, the higher the density, the slower the particle moves. Maxwell-Boltzmann distribution of speed also basically shows the probability of finding a molecule at a certain energy state. It basically looks at the velocity, the fraction of molecule moving at a certain speed. So it basically gives an idea as to where you can find a molecule at a given speed. The root mean square speed is a representative of all molecules in the box. So it basically would represent the mean speed of all molecules that is confined within that box at a given time. Here we can see the average speed of each molecule, and here we can also see the most probable speed of each molecule as well. The mean path is the average distance a particle travels between collision with another particle. So in essence, you're trying to assess how far or the path in which one molecule takes before it actually collides with another. And that's basically the mean free path. In air at room temperature and atmospheric pressure, the mean free path is about 70 nanometer, a value 200 times larger than typical radius of a small molecule like nitrogen and oxygen. So the mean free path is very small, which means that these molecules are in constant collision. For comparison, the molecule in a liquid typically have a mean free path roughly the same as a molecular radius. When we consider the cubic relationship of volume in distance, the difference in volume is in the order of 200 to the third power or 8 times 10 to the 6. So the volume of empty space in a gas at room temperature and pressure is on the order of 1 million times greater than the molecule of the individual molecule. This assumption is in the kinetic theory. We know that gases will condense if we lower the temperature sufficiently. The reason for this is that at lower temperatures, the kinetic energy of the molecule decreases, and eventually the strength of the attractive force between molecules will become comparable to the kinetic energy. And remember that kinetic energy is a type of energy that is associated with moving objects. So the faster the object moves, the greater the kinetic energy. So if you're running down the street, the kinetic energy that is emitted is higher than a person who is actually walking. So the higher the temperature, the greater the kinetic energy. The lower the temperature, the lower the kinetic energy. So with an increase in kinetic energy, at that point, molecules will begin to experience sticky collision. So if you increase the temperature and the molecules are moving much faster, which means that there is higher kinetic energy, at that point, molecules will begin to experience sticky collision. This means that pairs of small clusters of molecules might stay in contact for a short time rather than undergoing simple buildup billiard ball collision. This tendency for molecules to stick together will reduce the number of times that the molecules collide with the walls of the container. So the pressure of the gas will be lower than that predicted by the ideal gas equation. So when there is increased movement, so with increased movement or decreased movement of gases, you basically will have an increase or a decrease in the temperature, or an increase or a decrease in the pressure, because remember, the increase in pressure is due to the rapid movement of the gas particles or the molecules within the space in which they're contained. When the postulates of kinetic energy theory are not valid, the observed gas will not obey the ideal gas equation. So remember, the situation for a gas is not always ideal. In an ideal setting, we use the ideal gas equation. In a different setting where there is the influence of temperature, there's the influence of kinetic energy, where there's a change in pressure or a change in temperature, the ideal gas law no longer applies. So when the postulate of kinetic theory are not valid, the observed gas will not obey the ideal gas equation. In many cases, including a variety of important engineering applications, gases need to be treated as non-ideal. An empirical mathematical description must be devised. There are many equations that may be used to describe the behavior of a gas. The most commonly used is the van der Waals equation. If it's German, it would be van der Waals equation, is used for the behavior of gases in a non-ideal state. We have A and B, which are called the van der Waals constant, because A and B are constant. Unlike the universal gas constant, which is R, the values of each van der Waals constant must be set for each specific gas. If a gas behaves ideally, both A and B are 0, and if the van der Waals equation reverts to the ideal gas equation, investigating the connection of this equation to the ideal equation further, we see that the term involving A accounts for the attraction between particles in the gas. The term involving B adjusts for the volume occupied by gas particle. Consistent with its role in accounting for the volume of molecules themselves, the largest volume of A list is that of hydrogen fluoride. This means that compared to other gases, hydrogen fluoride molecules interact with each other more and require larger correction from ideal behavior. So here we can see a list of van der Waals constant for the van der Waals equation for common gases. In example problem 5.1, we considered a methane storage tank with a volume of 49.1 liter. When empty, the tank has a mass of 55.8 kilograms, and when filled, its mass is 6.07 kilograms. Calculate the pressure of methane in the tank at an ambient temperature of 21 degrees Celsius using both ideal gas equation and the van der Waals equation. What is the percentage correction achieved by using more realistic van der Waals equation? So here we can see you minus the mass of the methane of the full cylinder versus the mass of an empty cylinder. We find the mole of the mass as well in grams of methane, and also using the ideal equation we find the pressure of methane in the tank at a specific temperature, and using the van der Waals equation we find the constant of A and B of methane 2.25, 0.42, and using the van der Waals equation we have the number of moles, which is 388 moles. We also have the constant, which is 0.08206, and the temperature in Kelvin, which is 294, divided by the volume, which is 49 liters, minus the number of moles times the constant B, which would give us 388 moles, and the constant for A as well, divided by volume, which basically gives us 148 atmospheres. So the percentage correction would be, from the ideal situation, 191 atmospheres, minus from the actual situation or the van der Waals equation 148, divide by 191 times 100, the percentage correction would be 23%. One way to describe the concentration of a gas, of course, is to report its pressure or partial pressure, although a mercury barometer quite similar to one that might have been used hundreds of years ago will allow us to monitor the weather. It will not be of much help here. Instead, we will need to rely on a number of more modern instruments that offer fundamental advantages over a barometer. One sensor frequently used to measure pressure in the laboratory is a capacitance monitor. One way to create a capacitor is to position two parallel metal plates with a space between them in such an arrangement that the distance between the plates determine the capacitance. A capacitance monitor is based on a capacitor in which one of these plates is actually a thin metal diaphragm and the other is fixed and rigid. A capacitance monitor is based on a capacitor in which one of these plates is actually a thin metal diaphragm and the other is fixed and rigid. So here we have a schematic diagram. The tube on the left is connected to the gas sample whose pressure is to be measured. So the gas molecule will enter here and strike the diaphragm, and the force of the collision determines the space between the diaphragm and the fixed electrode assemblies. So between the plates is kept under a vacuum. We connect the sensor so that the other side of the diaphragm is exposed to the gas whose pressure we want to measure. One side has to be exposed to the gas and the other side has to be exposed to the sensor. So the pressure on the gas actually will produce a force on the diaphragm, causing it to bend towards the second fixed plate of the capacitor. This in turn changes the capacitance of the device. If we construct an electrical circuit in which the capacitor is one component, we can measure a voltage in that circuit that will be related to the pressure applied to the diaphragm. To make the sensor easy to use, the circuit can be distinguished so that we can measure a single voltage whose value is directly proportional to the pressure. Monitoring the voltage allows us to see any changes in pressure. So here we have the electrode that will basically be a voltage monitor, and here we have the vacuum as well. Capacitance manometers are most often used to measure pressures in the range of 0.001 to 1000 torr. This range includes moderate level of vacuum frequency encountered in the laboratory. One advantage of this type of gauge is that it has virtually no moving part as long as the diaphragm is not damaged. The gauge should work reliably for long periods of time. Both the barometer and the capacitance manometer respond fairly directly to the force exerted by gas molecules, but not all pressure sensor will work that way. A useful pressure measuring device can be based on any gas property that varies predictably with pressure. A thermocouple gauge measures pressure between 0.01 and 1 torr, for example, are frequently measured about 1.0 torr. A thin filament is heated by passing a fixed electric current through it, and the temperature of the filament is then measured using the device called a thermocouple, as we can see here. The filament is in contact with a gas whose pressure we want to determine. As the molecules in that gas collide with the hot filament, they tend to carry away some energy, reducing the filament temperature. The higher the pressure, the more molecules will collide with the filament and the lower its temperature will be. The thermocouple produces a voltage that is related to the filament temperature and therefore to the gas pressure. Capacitance monitors can be effective to pressures as low as 0.01 torr. This is a very low pressure, just over a millionth of an atmosphere. But in certain types of experiments, such as studies of extremely clean metal surface, laboratory vacuums as low as 10 to the negative 11 torr are necessary. At such low pressure, it's no longer feasible. So this is a schematic diagram of a thermocouple gauge. An electric current heats the filament and the thermocouple monitors the filament temperature. Gas molecules collide with the filament and cool it. So the higher the pressure, the lower the filament temperature will be. A readout circuit usually converts the measured filament temperature into pressure units for display. So this is used to measure the force produced by a molecular collision. So here we can see the molecules or the ion, and we have also the ion collector. So the gas would enter here. You have the hot filament, the electron collision grid, and electron collection grid, and And this is basically a schematic diagram of an ionization gate where electrons emitted from the hot filament collide with gas molecules and knock an electron free. The resulting cations are collected at the center of the gauge, and the current they produce is a measure of the gas pressure. So the current that they produce is a measure of the gas pressure. Finally, this marks the end of our lecture today. Feel free to ask your questions. I'll be available to assist with practical sessions and tutorial, and I'll see you for the next lecture.